These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. Thank you. We know that this would be called an alkane. What's the name for this type of functional group?
Alkyne.
One lesson is that carbon-carbon double bonds are considered functional groups. Even though they only consist of carbons and hydrogens, we can still consider those a functional group. And what's the name of this functional group?
Alkyne.
Alkyne?
Or kene, whatever.
Alkyne would be the right way to pronounce it. Alkene would be the double bond. So this would be alkyne. What is the hybridization of this carbon?
SP.
That's why it's
That's why you have to draw it
linear.
like a line.
That's right, you read my mind. This would be sp2, which means that the geometry of both of these carbons is linear. So you can't use, in a sense, you can't use the normal bond angles in a bond line notation. You can't draw this like normal bond line notation. There has to be this linear arrangement here when you have an alkyne. So how many carbons have I drawn in this molecule? 5. 1, 2, 3, 4, 5. It's easy, I think, to forget the fact that there's carbons over here or to miscount the carbons. Maybe, therefore, when you're working with an alkyne, maybe it's best to move away from the bond line notation a little bit and actually draw in the alkyne carbon. It's probably a good idea to actually draw in the alkyne carbon because otherwise we could get confused about that linear arrangement.
Which one's better, like more prioritized? Triple bond or double bond?
You mean for nomenclature?
Yeah.
For nomenclature, the double bond gets a higher priority. By the way, that reminds me, you guys have the second language books. And one thing that we said is that the one chapter in the second language book we've kind of skipped is the chapter on nomenclature, because that chapter does all the nomenclature for the semester at one fell swoop, whereas you guys learned the nomenclature step by step. But now that you're preparing for the final, which might cover nomenclature from the whole course, you might actually find it useful to go through the nomenclature chapter of the second language book now, because that covers in a unified way all the nomenclature you've seen all semester, including alkenes and alkynes. At this point, any part of the second language book would be relevant. So if there any chapters you haven't gone over, this might be a good time to review those. What's the hybridization of this carbon?
SP3.
This one here?
SP2, sorry.
And this one?
SP.
Right. Now, where do electrons prefer to be? In an s orbital or a p orbital?
S.
S. You know that when we're using the Aufbau principle and filling up shells, we usually fill the s before the p. For example, we would fill the 2s before the 2p, or we would fill the 3s before the 3p. So the electrons must prefer to be in an s rather than in a p. Well, which of these hybridizations has the most s character? sp3, sp2, or sp? This has the most s character. How much s character does it have? 50%. Whereas this is only a quarter s character. So where would an electron most like to be? Alkanes or alkynes?
Alkynes.
Electrons prefer to be here. Does that make this carbon the most electronegative or the least electronegative? Yes. So this is something you might not have ever heard before in chemistry. The same element can have different electronegativities if it has a different hybridization. Different hybridizations give you different electronegativities. sp gives you the highest electronegativity because it has the most s character. And sp3 is the lowest electronegativity because it has the least s character. So who wants the electrons the most? The one with the most s character, which means it's the most electronegative. We're still not saying the carbons are really electronegative, but the sp carbon is more electronegative than an sp2 or an sp3. Well, the consequence of that is let's say we have a base. Let's say we have a base. What does a base like to do? It likes to take a proton. But it can only take a proton that's willing to leave. In the past, we've said that bases like to take protons from electronegative atoms. We've said that bases like to take protons from electronegative atoms, like maybe oxygens or nitrogens or sulfurs. So would it be likely that the base could take the proton from this alkane? Hi. Hello.
Yes.
Yes.
Oh, no, because it's not electronegative.
Oh, yeah, it's not.
That's right. This is an alkane carbon. It's not electronegative. Remember that of the nonmetals, carbon is just about the least electronegative. Carbon is less electronegative than an oxygen or a nitrogen. So this is not a favored reaction. This usually doesn't happen. I'm going to X this out.
Why would it be a minus instead of plus?
Well, let's see. Do these electron pushing arrows make sense? The base is taking the proton.
No, I'm talking about the carbon chain.
Now, when the proton leaves, it leaves its electrons behind. When the proton leaves, it leaves its electrons behind. After all, remember, what's moving is a proton, H+. When you lose your H+, you become negative. That's why the base started neutral. I'm sorry, the base started negative, and now the base is neutral. So the base has, in a sense, donated its negative charge over here. Remember that the Lewis base definition of a base is an electron pair donor. Bases are electron donors. So if you get attacked by a base, you should end up more negative. That's pretty important, actually. That's the reason that bases are similar to nucleophiles. Both bases and nucleophiles tend to donate electrons. All right? So the important idea here is this reaction generally doesn't happen. We haven't really, anytime we've had strong bases, we didn't think of the base as just deprotonating a normal alkane carbon. And the reason it doesn't happen is it would leave a very unhappy negative charge. This is a very unhappy negative charge, so we wouldn't make it in the first place. However, let's see what would happen. If we deprotonate this carbon. If we deprotonate this alkyne carbon, wouldn't that give us something that looks like this? Well, this carbon is still not thrilled to have a negative charge, but is it more or less happy with the charge than the alkane would be? More. This is the idea we were just reviewing a second ago. We were reviewing that sp carbons are more electronegative. We were reviewing the important idea that sp carbons are more electronegative. You guys might not have seen in the past the idea that different elements, the same element has a different electronegativity if it has different hybridization. Changing the hybridization changes the electronegativity. And sp carbon is more electronegative than sp3. Therefore, we actually can make this anion. We can make this anion because this negative charge is much more stable than this negative charge over here, because this carbon is much more electronegative than this one. I crossed this reaction out to show it wouldn't really happen. This reaction generally doesn't happen, but this reaction does happen. If we have a good base, we can take off the proton, and that puts a negative charge on this carbon. So this is going to be an important reaction for us. What that means is that alkyne hydrogens are somewhat acidic, because an acid is somebody who's willing to react with a base. So what this tells us is that alkyne hydrogens are somewhat acidic, whereas alkane hydrogens really are not acidic at all. Why is this interesting? Well, what can we do now with this? Would this carbon now act like a nucleophile or an electrophile? Nucleophile. We're always interested if we can find ways to make carbon nucleophiles, because it's much easier to make carbon electrophiles. It's easy to make a carbon electrophile by putting a halogen on it, say. There's far fewer ways to get negative carbons. We already learned how to make Grignards, for example. Well, this is another way that we can get a negative carbon, and the nice thing about that is then we can form larger carbon-carbon chains by having a carbon nucleophile attack a carbon electrophile. You do need a pretty strong base for this to work. The common bases are sodium amide. We know this is a pretty strong base, N minus. Or you could use a Grignard or an alkyl lithium.
If you would have excess NaNH2, would it completely take away the H's? Like, would it make it into a simple alkane?
Completely take away the H's. Well, first of all, this only takes away alkyne hydrogens. And there is only one alkyne hydrogen.
Oh,
Right?
okay.
It's not going to take these hydrogens because they're not alkynes.
Okay.
We can only take the alkyne hydrogen. These carbons are not very electronegative. In any case, once you take away one hydrogen and you have a negative charge, it would be really hard to give this a -2 charge. -1 charge is pretty much all we're ever going to see.